Great. Welcome to the last invited talk, and definitely please watch the invited talk and then attend the poster session right after on Galilee. But this invited talk is from Sheila Seidel. She's from Boston University, and she'll be presenting on non-line of sight imaging. Sheila, please take it away.
Okay, hi, I'm Sheila Seidel, and I'm going to talk about the vertical edge occluder as a powerful tool for forming non-line of sight images. So I just want to open with asking everyone a question. If you think we should be able to form a reconstruction of what's going on around this corner using a photograph of what's in this green box. And this is exactly the kind of imaging that's enabled by the vertical edge occluder. So the ability to form non-line of sight images could be really useful in a lot of different applications. This includes autonomous vehicle navigation or robotic navigation, search and rescue applications. And in the common scenario where the occlusion is a wall, light from the hidden side is cast onto the floor on the visible side, forming what we call a penumbra. And in this work, we're interested with taking photographs of this region and forming reconstructions of the hidden side. So what gives rise to the penumbra? So basically, I'm showing a bird's eye view of our scenario. If you put a point source in the hidden region and draw a dotted line between that target and the edge, you can see that everything to the right of the dotted line is illuminated by the point target, but everything to the left is actually occluded by the wall. And we can put another point target in there and see that this edge gives rise to these fan-like penumbra patterns. The first work to really exploit these penumbrae was by Baumann et al. And here they're forming 1D reconstructions where that one dimension is azimuthal angle around the corner of hidden scenery in motion from a video sequence. And it's moving parts of the hidden scene because they are performing background subtraction. In our own subsequent work, we form 1D reconstructions of moving and non-moving hidden scenery because we're not performing background subtraction. And we do that using a single snapshot without assuming a uniform floor albedo. In this talk, I'm going to focus on 2D scene reconstruction from a single photograph. So our new reconstruction dimension is range into the hidden scene. First, I'm going to talk about our prior work in relevant background. Then I'm going to discuss our 2D non-line of sight estimation from a single photograph. And then I'm going to discuss edge-resolved active imaging systems that are now happening. So many of you may be familiar with the original corner camera work of Katie Baumann. And what was achieved here was 1D reconstruction of hidden scenery in motion, and they're using background subtraction. So you can see the setup here. They have this tripod looking at a region on the floor of the visible side. And then on the hidden side, there's people walking around wearing different colored clothing. And in these reconstructions, you can see each column of the image is a single 1D reconstruction of hidden scenery in motion. And so here's the one person scenario with the person in the blue shirt. And then there's a blue and red shirt scenario in the bottom right. In our own subsequent work, we demonstrate 1D reconstruction of the entire hidden scene from a single photograph without assuming a uniform albedo. And we show in our paper that even with background subtraction, Baumann's algorithm suffers performance degradation when the floor albedo is not uniform. And in our own static scenario where we're not performing background subtraction, it's even more important to consider non-uniform albedo in our forward model. So in our forward model, you can see we're writing our measurements in terms of F, a vector of unknown floor albedo, which we're going to estimate, and V, our 1D hidden scene as a function of azimuthal angle. And then we write our optimization problem in this way, where we have a data fidelity term. And then in this work, we rely heavily on regularizers for the scene and the floor albedo. So just to give you a sense for what this looks like, here's a line of sight view of the hidden scene. And we take a measurement that looks like this on a very patterned, non-uniform floor and are able to form a reconstruction that looks like this. You can see in the plot, we're showing our 3 different color channels and then the composite RGB image on top, and there's very close match there. Another very relevant work is by Saunders, Murray, Bruce, and Boyle. And here they have an occluder of known size and shape. And it's 2D, and they're using that to form 2D reconstructions of the hidden scene. So here is their camera, and they're looking at this visible wall and trying to recover this hidden scene. And with a measurement that looks like this, they're able to form reconstructions that look like this. So there's very close match there as well. And in this work, they also introduced the concept of computational field of view. And so they basically show that the regions of the hidden scene that are best conditioned for recovery are those from which projections of multiple occluder edges fall. So in our work, we're using this 1D vertical edge occluder. And our question is, with this 1D occluder, are we fundamentally limited to 1D reconstruction? And so what I'm going to show in this talk is that we are not fundamentally limited, although range is certainly challenging to estimate. Okay, so in this work, we start with a point target analysis to better understand the merit of this edge occluder and the challenge for 2D reconstruction. So we parameterize the hidden side of our scene in cylindrical coordinates. We have a range from the corner and azimuthal angle alpha. Z is the height measured out of the slide. And then our approach is to derive the Kramer-Rao bound for localizing a point target at location rho s azimuthal angle phi s and at 0 height. And so I'm going to show you some sample results from some simple scenarios. And in all results that I'm going to show, I'm also going to compare to the case where we have no edge occluder, just so we can understand the benefit brought by that edge. So here's a bird's eye view of a scene, and you can see a point target at range rho and azimuthal angle alpha. And with no edge in place, you can take a photograph here on the floor, and it might look something like this, where you can see very subtle gradations in the measurement due to the radial fall off of that target. And then we can use our Kramer-Rao bound tools to derive uncertainty regions around this point target location and other point target locations on a polar grid. And so here's what that looks like. And you can just see that it's equally difficult to estimate range and angle here. And also, as you would expect, it's more challenging to localize a target as you get further away from the measurement. So if we put our edge in place, now our measurement looks something like this due to that yellow point target. And you can see we have that penumbra in our measurement, and the corresponding uncertainty regions actually look like this. So you can see now, even though I promised these are bubbles, they actually look like lines because the angular uncertainty is so low due to the resolving power of that vertical edge. And I also just want to point out that as you move deeper into the scene in angle, so like over here, the range uncertainty is actually greater with the edge in place. And that's because if you look at that measurement in the bottom left, you can see there's fewer pixels actually affected by that point target. And so it's more difficult to use the radial fall off patterns to discern the target range. The story actually changes a little bit when we have a more complicated scene with multiple targets. And here, the edge occluder separates light from different targets, making range easier to estimate when we have our edge in place. So here, we're going to fix one target at a range of 1.5 meters and at an azimuth of pi over 4. And then our second target we'll fix at 1 meter, and this one will sweep an azimuthal angle phi 2. And on the right, I'm showing the Kramer-Rao bound for these two targets, unknown ranges. And the top two curves are when we have no edge in place. And you can see, as predicted by the last slide, that it's more difficult to localize the further target. And also that both of these curves are much higher. The uncertainty is higher when there's no edge than when there is an edge now. And that's true at all angles except for when these targets are at the same azimuthal angle. And the reason for this is if you look at the bottom left, there's actually now a swath of pixels affected exclusively by target 2. And so it makes it easier to tease out the radial fall-off patterns from these different targets and estimate their range. So you might have looked at the last few slides and thought, you know what, angle is very easy to estimate from this edge, but range is much more challenging. Why are we trying to incorporate range into our forward model? So I'm going to use a toy scenario to try to answer this question. If you look at this simple scenario, we have our occluding wall, a hidden side that's composed of one simple white cylinder, and this is where we're going to collect our measurement. And in a really high SNR scenario, it might look something like this. If we assume that everything is in the far field, here's what our 1D reconstruction looks like. And you can see there is a peak at the angular location of the target, but there's also artifacts at angles where there clearly is no scene content. And then if you look at the residual, there's a lot of undescribed radial fall-off patterns in our measurement. So if we choose to estimate range and incorporated it into our forward model, now we ultimately arrive at an estimate like this with way fewer artifacts, and our residual is much smaller. So we're adding a new reconstruction dimension and improving our 1D reconstruction as well. So for a forward model, we parameterize the hidden side in cylindrical coordinates, like I mentioned before, and for the visible side, we're parameterizing in polar coordinates. And we'll describe the light outgoing LO from floor point P as the sum of incident light on the floor from the visible side and incident light originating from the hidden side. And then we'll multiply it by the albedo at point P, which in this work we do assume is uniform across the observation region. LH is the sum of all light coming from the hidden scene, attenuated by radial falloff. And you can see the d squared in the denominator, where d is the distance along the floor between point P and seen element at range rho and azimuthal angle alpha. And here, SH bar is that 2D plan view that we seek to recover with our algorithm. And you can see we're integrating out across height z. So to further model occlusion in the hidden scene and make this problem more tractable for us, we assume that SH bar is separable in range and azimuthal angle alpha. And so we can write it in this way, where SH alpha is the scene radiosity as a function of angle. And so for a simple scene like this with one target, here's what that might look like. You can see a peak in intensity at the angular location of the target. And then rho H alpha is the scene range as a function of angle. And so now at most we're estimating a single range and intensity per angle. So now we have our continuous forward model, which we've written in terms of this 2D plan view that we seek to recover SH bar. And we can write our discrete forward model. And now, in addition to assuming that SH bar is separable in range and alpha, we're also going to further make this problem easier for ourselves by assuming that the hidden scene is comprised of Q unknown hidden targets. And so under this assumption, SH bar can be described in terms of Q unknown ranges and Q angular extents, and then a 1D radiosity as a function of angle. So for this hidden scene, we've got two targets, Q equals 2, and now we're just estimating two ranges and two angular extents, and we'll have a higher angular resolution reconstruction in V. So our objective function has a data fidelity term. We're also promoting sparsity of the scene in a wavelet basis, and then also positivity of our range and scene estimates. And we minimize this by an alternating method. So here's one measurement scenario and a corresponding result. So you can see we have two targets in our hidden scene, the measurement in the bottom left. And in our reconstruction, we have really high angular resolution, sharp boundaries between the different colored regions on the objects, as would be predicted by our CRB. And then we also place the two targets correctly with respect to each other in in range. And so if you look at the measurement, maybe you can see where they are in angle, but it's very difficult, if not impossible, to look at that measurement and tease out range with the naked eye. We also recognize that these results have only been tested in a constrained environment. So in this paper, we explore how weak the signal can actually be and how this still works. So here's a high SNR scenario with the hidden scene on the left. And if we add more ambient light, you can see that our range estimate does degrade, but the angle is still very spot on as predicted by our Kramer-Rao bound. So range is fundamentally harder to estimate. So I'm going to change gears now and talk about active edge-resolved imaging systems. And the earliest one of these is the edge-resolved transient imaging system, or ERTI. And here they're deriving longitudinal resolution from the temporal response of a pulse laser and angular resolution from that vertical edge. So you can see here, they're pulsing a laser at the floor and scanning it in a small arc around the corner. And then a single pixel SPAD is pointed at the pink region on the floor, and that accumulates histograms of photon arrival times. And then if you look here at subsequent scan spots, you're illuminating slightly more of the hidden scene. And so by differencing subsequent histograms, you can start to isolate scene content in a given angular wedge. And so they use reversible jump Markov chain Monte Carlo algorithms on the measured data to reconstruct reconstructions like this. So I'm also currently working on a new edge-resolved active system, which we're calling motion-enhanced edge-resolved transient imaging. And so actually, due to the longer scan time of ERTI, that system's liable to miss motion in the hidden scene. And this new proposed system will hopefully produce robust reconstructions of changes in the hidden scene in real time, and it's designed to work with very high levels of ambient light at low signal counts, which I'll demonstrate for you on the next few slides. So in this configuration, we're now pointing a SPAD array at the floor at the base of this occluding edge. And we're going to pulse a laser on the floor adjacent to that edge. And our goal is to reconstruct hidden scene using changes between measurement frames. So here's a side view of the hidden scene. And in our measurement, we're going to have rates due to just the stationary background and scenery that's shown in yellow here. But if before our measurement frame, somebody enters the scene or an object moves into the hidden region, we're now going to have rates due to the introduction of the foreground objects. And actually, in addition to that, because of occlusion within the hidden scene, now we're going to have a rate reduction due to the region in the background that's occluded by that new green facet. So our reconstruction algorithm seeking to reconstruct and track objects in motion and also reconstruct this blue region and paint in the background behind where motion is occurring in the hidden scene. So here's what that'll look like as someone enters. We'll find their location and also describe the background behind them and slowly paint a picture of the hidden scene. So I'm going to show a very early proof of concept here. Here's our synthetic scenario for one frame. We've got the walls in the background, and this foreground object has just entered, blocking this region in the background. And we're going to try to reconstruct both the foreground and background regions. And to give you a sense for the measurement rates that we can handle here, I'm showing the rates at a few different camera pixels here due to that foreground object. And you can see we peak out at 6 photons per pixel. And then the background rates in that region on the background are even weaker at less than a photon per pixel. And here's what our measurement histograms look like, very noisy. We've got counts due to the background walls, the small signal, and we're also simulating a very high ambient light level here of 10 photons. Okay, so using this very noisy and challenging synthetic data, we can test our proposed reconstruction algorithm. So our first step is to apply passive 1D techniques to determine the angular location of motion in the hidden scene using the techniques I talked about earlier in this talk. Our second step is to use Markov chain Monte Carlo methods to estimate the parameters that describe the foreground and background regions that have changed. And the first step here is first we estimate our foreground object. And you can see our algorithm arrives at a very close match there. And then we also estimate the background. And the same thing happens here. Oops, I just ran it again. And that's despite the very low signal and very high ambient light. Okay, so in conclusion, I've discussed our single snapshot passive edge resolved imaging work. And we had our 1D recovery of stationary and moving hidden scenery without assuming that the floor is uniform. And then I discussed our 2D reconstruction work. This included our point target analysis to understand the challenge and feasibility of this kind of reconstruction with the edge. And then also I introduced our new forward model, showed you our optimization framework and some recovery results. And then I also just proposed a novel motion-enhanced active edge resolve acquisition strategy. And I showed you a very early proof of concept there with very high ambient light levels. And I want to just finish by pointing out that edges and walls are ubiquitous. And this opens the door for some really exciting non-line of sight imaging systems. And so for those who are interested, you can check out our papers.
Thank you very much for this great talk, Sheila. Really enjoyed it. It's a very nice culmination because looking at your results, it seems like there's a lot of real world translations and kind of demos that can be done in kind of low resource settings, which is kind of unique for some of the talks here. So I read on your website that you're looking at educational programs as part of this research as well. So can you expand a little bit more about how you're going to connect non-line of sight imaging to kind of a younger audience?
Yeah, that's such a good question. And it's something we're really excited about because Katie Bauman's original corner camera, you look at that and it seemed magical. So we're going to try to use some of these results that seem so cool to try to get people excited about STEM. And what we have in mind is twofold. First, there's this box that we're making for kids to kind of build their own edge occluder in the classroom, and they'll be able to take a photograph with their mobile phone and reconstruct a scene that they set up on the hidden side of their box. And then we're also working with some undergrads at BU to work on an app like that will hopefully let people try this out in their own hands on their iPhone.
Wonderful, wonderful. And that's on the educational component. Maybe I think you have a very good visibility on this, given that you've been working on this topic for a number of years. 10 years from now, what is non-line of sight imaging going to look like? Is it going to propagate to mainstream CVPR? Is it Is it going to go into products? What do you think?
I think some of it could definitely go into products. Like Katie Bauman's corner camera is very robust. Some of my single snapshot stuff is a little less robust, but the last active system that I talked about, we're very excited about because we think it could be deployed to very real world scenarios. And there's certainly like a very active need for this with self-driving cars. So I am hoping that some of these systems will find their way into products.
Great. Thank you so much for this talk, Sheila. But before we quickly sign off, let me just mention that the poster link is in the chat. There's a Gavely link that David is going to put in. And there's also going to be one more keynote after the poster session, so do try to stay for that. It'll be a keynote by Paul Debovic. Thank you so much to all the speakers in this session.